All right, how you doing? This is Evan Sorelli here with T Equipment. I'm the Vice President, one of the founding members of T Equipment. We're here today hosting RIGOL. Chris Armstrong, the Director of Marketing, I believe is the title. The seminar is going to be mostly dedicated to multi-domain debugging. Just a little bit about T Equipment. T Equipment is a distributor based in the U.S. We have multiple warehouses across the country. We have a technical staff of engineers inside our offices so we can support customers through application questions right on through a support process. We handle a whole domain, a whole range of different product ranges, a lot of different industries, a lot of different product groups. We have product managers that manage various products and product groups and application specialists for all the different types of test equipment that we sell. Ranges a whole range of different industries and different types of equipment. The core is really benchtop test equipment, R&D type equipment. With that little intro about T Equipment, I'm going to hand it over to Chris here, and he'll start the webinar. Any questions, feel free to ask them in the question panel or in the chat. Thank you. Chris, I'm making you the presenter right now.
Thanks, Evan. So as Evan said, I'm from RIGOL Technologies. I've been with RIGOL for about 9 years, working on different projects. And what we wanted to talk about today is really some multi-domain debugging challenges with the ongoing changes and IoT integration work being done across a number of industries. Many engineers are adding RF capabilities to their existing embedded products. They're adding new products with Wi-Fi and Bluetooth and other RF capabilities. And these integrations cause a set of problems that are difficult to debug traditionally, right? Because they cross what we call these domain boundaries between RF and analog digital. And so we're going to look at some ways today, some technologies that RIGOL brings to enable this kind of debugging, and then some of these challenges that we'll look at in a couple different examples. So first off, we're going to be doing some of this with slides, but we're also going to be doing some with the webcam here. So I've turned on the webcam. You should now see a little image of the spectrum analyzer there. So we're actually going to switch between the spectrum analyzer and the oscilloscope a couple different times as we walk through some examples today. So when we do that, you can change the size of your screen for your webcam view there to see more closely what we're doing. So both of these instruments we're using today have an HDMI output that I'm using into a webcam tool. So that's allowing us to see exactly what's on the front panel of the instrument really in real time. So as I said, we're going to talk about first some of the RF technology, or what we call UltraReal technology in our real-time spectrum analyzers, what that enables, our UltraVision 2 technology in our oscilloscopes, and how we use some of those tools to really take this sort of multi-domain debugging to the next level, how we've sort of integrated the triggering and the setup of these devices, and then walk through a couple of, I think, key examples that really tell us more about important factors in debugging across domain and ways we can speed that process. So UltraReal technology exists in our RSA 3000 and 5000 series instruments, and really a couple key factors that this enables that makes it possible to use in this way. We're able to do up to 146,000 FFTs per second. We'll see why that's important in a minute when we hit a couple of key specs. We can view up to 40 megahertz in real time across the screen. We have what's called a 100% POI, or probability of intercept, that's down as low as 7.45 microseconds. And we're going to talk for a minute about why that's important too. A couple of key specs here in how fast we can process the FFTs and what the probability of intercept really means enables us to do a better job of seamlessly capturing data here when we're time correlating it with our oscilloscope. Of course, the visualization modes we'll look through in the examples. And then the IF output is critical in these tests as we're using that in the oscilloscope. And then, of course, advanced triggering and some of the swept mode capabilities as well that make the noise floor really perfect for these sort of tests. So what is the probability of intercept mean? What is 100% probability of intercept? So by specification, this is the shortest pulse length in time that's really guaranteed to be accurately measured in power, no matter when the pulse happens. So the instrument certainly will capture shorter pulses than this, and you'll be able to see them on the display. But this is the shortest pulse that you can guarantee accurate in power. And so that's really an important specification for just understanding what you're looking at. And again, the RIGOL here has in the best mode has a 100% probability of intercept on pulses as short as 7.45 microseconds. So we're actually going to be working below that threshold today for a few of our tests. We'll see what that means. This 100% POI is really defined by the span and the RBW settings of the instrument. So that's kind of complicated. So how is that calculated? What does that really mean? Well, here's a little graphic I like to use to sort of explain this. So as you see, you can see the 6.83 microsecond periods up there between FFTs. So that's in essence the inverse of 148,000 FFTs per second. So we have an FFT starting every 6.83 microseconds. So there's really two things I want you to be aware of here. One is, if you want to capture the shortest pulse as accurately as you can in power, you would use the little windows there, the RBW6 window. Because with RBW6, the pulse only has to last for, as you can see the yellow line there at the bottom, the 7.45 microseconds, a little longer than that 6.83 microsecond window. That way, because remember, this is entirely asynchronous, right? It's just continuously capturing FFTs. So that way, no matter where that pulse happens to land, in between or among the windows, it's always captured completely by at least one window. What we're going to use today is mostly the RBW1 and RBW2 settings. And you see why in this graphic, because in this case, RBW2, you have constant overlap, right? The red FFT starts before the blue RBW2 window is done. That means that every point in time that is captured by the analyzer is converted into frequency and used to display signal. So that means it's really what we talk about, seamless capture with the RBW1 and RBW2 settings. And that, I think, gives us the best feel for when we're time correlating this data over to the oscilloscope, we know we're not missing any events in the RF space. Now, again, we're going to be looking at pulses, down as low as a couple microseconds here. And so they're not going to be accurately measured in power necessarily. But in this kind of debugging, that's not what we're trying to accomplish here. What we're trying to do is really make sure we can visualize the signal, capture it and analyze it in both the RF and the time domain. So that's how we're mostly set up here today. And so really what you want to just realize about that is that using the seamless capture settings is most appropriate to making sure you're not missing any RF event. And that way you can see all the types of problems that might be both being output by your device, coming into your device, and affecting your operation as you're trying to do functional testing. So as I mentioned, we have really a number of different visualization tools on the spectrum analyzer that are part of this technology package that we're really going to be using today. We're going to use a lot of the density and the density spectrogram, as well as the PVT, and the last one there is the frequency mass trigger. So PVT is power versus time. So we'll see a few of these different visualizations as we walk through the examples. So that's on the spectrum analyzer side. That's the technology that we're going to be using today. Let's talk for a second about the oscilloscope. So here we're using a 7000 series oscilloscope that really is built on RIGOL's own UltraVision 2 hardware platform with our own RIGOL IP chipsets included. And this brings a couple of important factors to bear on this application as well. Most notably, we can get up to 10 gigasamples per second, which is really an incredible 20x oversampling on our 500 megahertz signal. So most of the signals we're going to be working with are right in that area, just below 500 megahertz, and we're going to be oversampling to really get the most out of that signal. But we also have the ability to capture 500,000 waveforms every second. We can record almost 500,000 frames, and we have up to 500 million points of memory. So we're going to show how those different capabilities and the different ways to make the memory useful really provide a unique capability in this sort of debugging. And of course, we have the advanced and zone triggering and the enhanced FFTs that'll come in handy as well. All right, so that's really all the product-based talk. So we really want to get into now the application space here and see, how can we define some problems that exist when integrating RF and embedded design into new products? How can we look at the types of problems that occur, and how can we ultimately solve them better? So first thing I wanted to just explain here is I've got two instruments on my desk here, real-time spectrum analyzer and an oscilloscope, and I've done a couple things to set this up. First off, I have the IF output, which is on the back of the real-time spectrum analyzer. That's going into channel 1 on our oscilloscope in 50 ohm mode. So that really allows us to see whatever the center frequency on the analyzer is brought down to a 430 megahertz carrier. So we're going to be able to look at that and then analyze that in the time domain down at 430 megahertz. We've also created a double-ended triggering here. The triggering on these two instruments is so flexible that we're able to set a trigger outline from the spectrum analyzer to the external input trigger on the scope, and we have a trigger out function on the scope that's able to go into the trigger input on the spectrum analyzer. So we'll use both of those as we try to solve different types of problems that we think require a different approach. So now we're into it. Let's try to just set some goals for what we're trying to accomplish here in multi-domain analysis. So just to be clear, we're trying to debug and analyze some time-correlated embedded signals with some RF events. We have some challenging problems or failure states that are happening across these domains. So we'll see some failure states in RF that are being caused by logic or analog channels, and we'll see some failures on the digital boards that are being caused by RF interference in a couple of different ways. So we're trying to time correlate those signals. We're trying to do analysis on these short duration pulses, and we're trying to really navigate and visualize these signals of interest in a number of different ways. So the real-time spectrum analyzer, again, is allowing us to look up past the bandwidth of the oscilloscope and really see carriers up to 6.5 gigahertz. So what we're going to be looking at today primarily is a couple different signals. One is going to be a true RF signal in the 2.4 gig band, and another is going to be an emission happening up at about 875 megahertz. So both out of the range of the traditional scope, but able to be captured in this way. So when we're debugging, when we're going through this process of problem solving, especially between domains, this kind of work is all about working backwards from our symptom to ultimately root cause to causation, right? So maybe we isolate a problem in the design, maybe a customer brings a problem to our attention, and we need to go dig into the complete system and look at the RF subsystems, the analog and digital subsystems, and really try to solve the problem. Obviously, this is challenging because when these symptoms and causes cross domains, there isn't an easy way to correlate and visualize these with kind of traditional benchtop equipment. Some of these signals you could see if you had a 10 gigahertz oscilloscope lying around, but again, trying to find ways to make it easier for engineers to test and debug these systems without having to get specialized equipment to do it. So today we're going to talk about typical examples that really fall into one of four categories. One I call a really transmission issue. This is where the root cause of our problem is happening too quickly to view in the RF domain, right? So we'll see some really sort of 50, 100 nanosecond sort of issues that are coming in, that are really happening in the RF. But to really debug it fully and figure out what's going on, we need to search through it and analyze it in the time domain as well. And we'll see some what I would call modulation errors, or issues where the symptom is a subtle modulation offset in frequency or amplitude or phase. It's really just too difficult to look at in the time domain and really visualize just with a scope. So, and then we'll see a couple of different types where what I'm going to call emissions anomalies, where really we have, in this case, we'll talk about some correlated, or rather some emissions that are coming out of our product and how we find the root cause of those to really improve our test sort of in a pre-compliance mode. How do we improve our device operation to get rid of these anomalies? And then susceptibility, right? In this case, we're having a failure. Really in the time domain, the digital logics are resetting. How do we track down the cause of that problem when it's really an RF susceptibility issue? All right, so our first example is this high-speed transmission error. So here we've got our symptom is we have an error in an RF pulse shape, but it's too fast to see with the analyzer alone. So at this point, try to open up your webcam there. Make sure you can see the spectrum analyzer, and we'll get a feel for what this signal looks like. So as you can see here, we're in a density view, and so you can see an occasional about once a second an RF pulse is happening here, and you can tell we're in the 2.4 gig band, and we're looking at 40 megahertz wide. So there's a frequency hopping sort of FSK signal here, moving around the 2.4 gig band. We're having an occasional issue with some of these pulses, so let's look more closely. So one thing we can do is go into our density spectrogram, and here we can see clearly the duration of these pulses as the waterfall chart sort of shows you how it's moving through. We can also in here switch over to our power trigger. So this now we're capturing just the pulses, not the blank time in between. So now we're able to kind of adjust that pulse, adjust that power level, capture those pulses as we see. Now we're triggering out to the oscilloscope and capturing some pulses there also. One other way we can view this signal before we move over to the scope is with the power versus time. So now the bottom of the spectrum analyzer display is the spectrum, as you can see from before. The top is really a time view. So that's 30 milliseconds from left to right from our trigger point. So we can see that these are actually happening about once a millisecond. So if I take my sweep view down to about 5 milliseconds, there we can see happening about once a millisecond. And now if we really zoom in as much as we can, down to 100 microseconds, you can see just on the left side there, very short duration pulse. So that pulse itself is really happening, is less than 2 microseconds long. So well below the POI of this instrument, but we're able to capture it consistently. But we're still having trouble really finding what's wrong with this signal, or what's happening occasionally that's making it concerning. So let's look over to the scope. All right, looks like that still goes. So now you can see the pulse shapes on the scope, and occasionally we get a pulse shape with a gap in the middle, right? So that gap is sub nanosecond, or about 50 nanoseconds wide. So really hard to detect on the analyzer at all, right? But there's a couple things we can do to really enable this and capture this on the scope side. First, let's find a couple ways to use the long memory capabilities. So first thing we can do is we can go out to our full 500 million point memory depth. And as you can see in the top of that scope, we're currently sampling at 10 gigasample. So that's allowing us to see this high frequency content really clearly in these pulse shapes on the scope. So we're at 500 nanoseconds per division. And again, this is the IF output from the spectrum analyzer that we're looking at. So we can zoom in, let's actually zoom out and go out to about millisecond per division here. So now we can see those pulses, and we can look at them clearly, and we can zoom in on them. And we're really able to do that because of our memory depth is such that we can capture all those important characteristics out at 2 milliseconds per division and look at that sequence while still getting all the pulse detail, right? So we're able to Nyquist sample these 500 megahertz signals out in time. So now let's look more closely at these failed pulses. One of the ways we can do that is with record mode. So instead of making one long 500 million point capture, if we set this back to an auto memory mode, what we can do is really record thousands of frames. In this setup, we can get about 10,000. And this allows us to see how the pulses change and how they sequence, right? So we can go back and we can play these pulses through, look at the recording and see when we're having these bad pulses and when they're having good pulses. We can also do a couple other things. If we go back to, let's go back to live mode here. Turn record mode off for a second. We can turn on our digital channels. So we're looking at a digital line associated with the board that's driving these signals. And we can start to look at the frequency independently of these different of these signals. So here we'll set our center frequency to 430 megahertz. That's what we're looking at, and our span to about 60 megahertz. So you can see the frequency, the independent frequency of each pulse. Let's turn on a little peak search there. Turn our threshold down. So you can see the frequency moving across that pattern, and we can see each signal. And then, we can record sets of those data as well. So really able to look at different patterns in frequency and embedded code to really see all the problems that might be happening and how we can then go ahead and debug them. So here, if we go find one of our failures, we can see a couple things. We can see what frequency that pulse came in at. We can see some of the modulation on it. We can also see down in the digital line, we can see an error seems to be happening on D4, right? We can see the little red subpulse in the center of the screen. So that's really driving that. So that's really the one of the root causes of this problem is that digital logic line that's driving the pulse output. So let's go back to the slides for a second. So again, we looked at those pulse sequences on the live instrument there and those pulse failures. So combinations of occasional errors and glitches that we can really now dig into and resolve by doing high-speed time domain analysis of those while also capturing them on the spectrum analyzer and pulling them down from that 2.4 gig carrier to a place where we can work with them. And again, so here's a quick shot of those two systems working together, right? And then again, being able to record and capture those pulses. So again, once captured, Then once we find it, once we're capturing it in the RF domain, we can then trigger it. Again, we're on the scope there. We're triggering from the external line, so we're triggering over when the spectrum analyzer triggers, and that's what's allowing us to capture the right pulse. And then we can see it in frequency space and time domain, and ultimately find the problem in the logic. All right, let's look at the next kind of error, next kind of problem we have. So this one is really more about modulation, right? So having a subtle problem in our frequency, as I reset the spectrum analyzer here for us. There we go. So being able to look at problems in frequency here and then capture them and investigate them in different ways. So instead of just looking at those pulse shapes, let's identify a single area here where we might have a problem. Let's go ahead and change our trigger mode here, in this case to frequency mask trigger. And then I'm going to build this little frequency mask, and there we see we can capture single pulses in frequency. So we're able to trigger, and then really at the same time, only on a pulse in a certain frequency. So you can see that's happening much less frequently. It's happening about once every 5 seconds in the right frequency domain. So now I'm putting the scope back to where we had it there. And now, going to center that up. So now we're able to capture the pulse in frequency using our frequency mask trigger and look at individual pulses that way. So as I go in over to my analyzer, 1 second. So that's kind of how we trigger on these signals when we want to look at a particular frequency and then measure its amplitude or make sure it's operating correctly in a couple different aspects, right? And here's an easy way to kind of look at that video in sequence. Probably best to do this side by side. So we can see as we switch over and capture the individual frequency mask on the analyzer on the right, we can then see its triggers on the scope always in the same frequency bucket. So now we can look at those broken pulses as they're triggering in individual frequency buckets. So being able to slice these problems either by frequency, by power, look at those pulse shapes, and then ultimately problem solve regardless of the cause. It's a great way to kind of capture and look at these signals. And then the last, I think, interesting way to look at this on the oscilloscope is with this kind of a signal here. So what we're able to do then, if we wanted to do a long-term analysis of all those pulses and either set up a mask or record them and see them over frequency, we can use a combination of the multiple FFT capability on the scope. So here the scope's actually set up 2 FFTs. One is the purple trace that you see as the sort of new most common trace, and we've got the Keller density FFT going in the back with basically the same setup. So that allows us to see where all of those pairs of signals are capturing. And so if you've been watching, you can notice a couple things here. One, we actually can see a little wider on the IF output than we can on the front of the analyzer. So we can see the pairs that were off the screen a little bit on our analyzer for us, and so we can really see here clearly that the signal is working in 7 different channels with an FSK modulation within each of those channel patterns. So that really allows us to then kind of verify the power levels and timing of each pulse, regardless of where it ends up in the spectrum, and debug it that way. Okay. So now let's shift gears a little bit over to more of our emissions kind of problems. So here in this case, what we have is we have a kind of an infrequent change, an infrequent emission issue that is our primary system, our primary symptom of the problem. So I'm going to open up that setup on the, you know what, we're going to go to 875 megahertz, set up our free run, and we're going to look for this problem in our signal. All right. So here we've got our signal coming up, and I'm going to switch our view a little bit here so that we have the best kind of look and feel here. All right. So as we see this signal, we can see some subtle effects happening really in the background here as we look at the subtle changes going on. So we can see that there's a there's a clock pulse here happening, but there's also some subtlety happening over time that's really affecting this. Oh, that's what I did wrong. So we go down to. Now we can see it a little more clearly. All right, so we can see an effect coming where over time there's a power buildup in this frequency band, and we'll see that in a second here. And so we can start to correlate what's happening down in the spectrogram as the power levels change over time. See some reset action as those power levels change. Let's look at it now kind of in a video where it's coordinated between the scope and the spectrum analyzer. So as we see, you can see the reset there happening in the middle of the spectrum analyzer. And when that reset happens on the spectrum analyzer, we eventually find a line on the embedded board where the scope's also resetting. So here we'll see the frequency reset happening on the scope here in a second as it resets. So this is going to go ahead and in the end we can measure this, and we can see that it's going from about 1 kilohertz up to 100 kilohertz and then resetting about every 30 seconds. And so being able to track that and then capture it and see the reset action on the analyzer is key. So here we are looking for what's causing this subtle effect visually in the spectrogram on the analyzer, and then really trying to track it over to the oscilloscope as well, and being able to find that sweeping event, that anomaly in the end. So we really did that by using a near field probe on our board. So we sniffed around for the area on the board where that signal was emanating from, and eventually by looking in the immediate area there, found the cause, which was one of the digital lines was fluctuating and resetting on us on that board there. And so that's really how we worked backwards from an emission anomaly, really to an FPGA problem. So that was part of our control loop in the FPGA there was causing that reset function. And so here we were predominantly using the we did some triggering on the scope, but we weren't really triggering in a combined way. This was more of a visual correlation, right? The slow timing of the pulse buildup really makes it such that you need to visually see kind of what's happening on your logic and what's happening on your spectrum analyzer as it develops over time. And eventually you can find that problem by really looking in the close area on the board there. So that's sort of the third type of problem where it's really a visual data correlation challenge. Now let's look at susceptibility. So here we can see in this short clip, there's on that same signal we were just looking at, we occasionally see an odd reset behavior. So instead of that smooth frequency cycle like we were seeing when we were looking at it in the last video, what we're seeing here is this sort of occasional clipping reset function. And so, this is really it's a functional failure reset of our board that's causing us problems down the line in our embedded work. And so, how do we find the root cause on this embedded problem? Well, we can capture it. We can easily trigger on these sort of pulses and these resets, by doing a couple different recordings on the scope side. So we can analyze what's happening. But we've looked through our embedded system. We've looked through all our digital channels. We don't really see what's driving this problem. We've talked to the software guys, and the FPGA code doesn't seem to be causing this kind of a problem. So we have to look further. And here's how we really track it down to using the spectrum analyzer. We can track it down to an RF problem. And so in this case, what we see is an occasional wideband pulse that's really from a relay. So this is the RF envelope of a mechanical relay that we've tested, and so really a problem like this can really get into your embedded system. So once you've built added RF capabilities and added some other components to your system, you can see these systems start to interact in sort of unexpected ways. And so one of them is the wideband RF envelope of certain devices like mechanical relays really can cause you problems on your high-speed embedded systems. So here we see we eventually, by triggering from the scope and triggering out to the spectrum analyzer and looking at the spectrogram history, we were able to capture, hey, there's an anomaly happening here, 5-10 milliseconds before this shutdown, that's really seems to be correlated. So we're able to hunt down this individual pulse action. So those are really the four types of issues that you can debug across domains. So we have problems that start in the RF domain with modulation issues, or with high-speed output issues, and we have problems that really where the symptoms in the time domain, like odd resets or other functional problems, and being able to then both look deeper at those problems with the analysis tools of the instrument, but also to cross-correlate into the other domains using some triggering and analysis tools that are perfect for these tasks. These two boxes together really make a great tool set for these kind of mixed domain debug challenges. Okay, so here we are finishing up. So let's again summarize just kind of one more time from a high level, right? What we think we've been able to do here at RIGOL is develop a couple of key technologies in UltraReal and UltraVision 2 that really in these modern products do a great job of working together to make these sort of multi-domain debugging both powerful and affordable. It's really a combination of the IF output capabilities, the triggering capabilities, your RF visualization and seamless capture on the spectrum analyzer, combined with then your high speed, high sample rate, useful memory analysis tools in the oscilloscope. Make a great match for these kind of tests. So we've got a couple things we're going to be sending out to everybody. One is we have a multi-domain app note that sort of follows what we talked about today, and we have an RF basics guide that's a very popular sort of primer piece that we'll make sure everyone gets a copy of via email if you registered for this event. And then, of course, we have next week is Electronica in Europe. We've got a couple of we got some new products coming up that we wanted to kind of preview here a little bit for everybody. And so one of the key things happening next week is we're going to be launching a new oscilloscope series that really brings this UltraVision 2 technology we've been talking about today, down to even more of these type of IoT integration and engineers who are working on these kind of problems, right? And so bringing these capabilities down to a 70 megahertz scope that starts at less than $1,000, while still has that 8 gigasample per second sampling, super deep memory, and the capabilities that we looked at today. So it's going to be a great new instrument series that I think will be perfect for these sort of embedded design challenges. And we'll be sending you some more information on that next week. And if you're interested or you have any questions, you can always reach out to T Equipment, to Evan or myself here at RIGOL. We're happy to answer any questions for you, but we have some time now as well. So if anyone had a chance to chat any questions in or want to talk to ask anything now's the time.
Hi, Chris. This is Evan. We have a couple questions here. If anyone needs any more or has any other questions, just feel free to put them in the chat. One of the questions: how does having a dual mode analyzer swept in real time make debugging easier?
So I think it's a good question. We didn't talk too much today about the swept mode analysis, but this analyzer, I'm sending it over now, does both general purpose mode and swept mode. And what I really find useful, and I was doing some of it live for some customers last night, is the ability to really do a full span sweep in a millisecond, like it's doing here, and then really be able to immediately pick out the area of interest, right? So here, for instance, we've got a little peak over there at 120 megahertz. That's really the root cause of that 875 megahertz harmonic we were looking at, is the clock noise, fundamental clock noise. And you can see the 875 coming up occasionally. So what we do is we really look at the full span first, identify areas of interest, and then we can switch over to real time and get our seamless view of really some impressive, both capability and depth on those signals. So I use the general purpose swept mode, both for looking at passive devices with the tracking generator, but also as sort of a first phase debug tool. Lets you make sure you're looking at the right band, you're not missing any big problems before you zoom in and look at a 40 megahertz span in real time.
Gotcha. Here's another question here. You may have already partially covered this question, but what other types of measurements and analysis does the scope make possible?
Yeah, so the scope, we certainly didn't use all the scope's capabilities today. I think there are a couple key things worth noting. One being, we talk about this instrument, as I switch over to it, as having sort of 7 instruments in one, and that includes things like we have a digital voltmeter, a counter timer. We can do power analysis. We've got a histogram. We didn't use a zone trigger on these signals today, but you have a nice graphical zone trigger you can use by just with your finger on the touch screen there, capture signals that way. And so really the ability to use all those different capabilities. We talked mostly about the different ways we can use the memory in single capture or in segmented memory. And then additionally, the search mode capture. So the other nice toolkit is really the ability to use the search and mark table. So when instead of RF pulses, once you're dug in on the embedded side, you can go ahead and look for runts or pulses, and you can search for multiple triggers within a capture and get sequences and sort of timing of events there in a more challenging way. So I think that's really the set of capabilities, analysis capabilities on the oscilloscopes.
Great. Let me see if any more questions filter in here. If not, that'll be the end of the webinar. We'll of course send out the app note and the information that Chris was talking about earlier, as well as follow up with information on the 5000 series that's coming out. Just looking right here. I think that's it, Chris. We appreciate your time. Anything else on your side, Chris?
No, thanks, Evan. Appreciate it.
All right. Thanks, everyone, for attending, and you'll get a digital copy of this as well as the other information that we talked about. Thanks, everyone. Appreciate your time.
Thank you.